Okay, everybody, so this is the last lecture of the course. This is lecture 24, and today I'm going to take a chance to back up again and provide a little bit of a review of the course, and so this will be a review of modern cosmology. I hope if you have any questions along the way, you go ahead and ask. Before I get going, let me say it's been a lot of fun. I hope you've enjoyed the course, and maybe I'll get to see you in another course again as soon as next quarter. So starting again, we're going to do this review of modern cosmology. This is a really cool picture. I think maybe I've shown it before. It's from Joshua Tree National Park, so it's not too far from here. And it's one of these great places still on Earth today where it's dark enough, and if it's clear outside, you can actually see the Milky Way and a lot of stars that you can't see from here. So if you haven't been out there at night, it's worth going out. It's beautiful. So you see the band of the Milky Way here arching over the sky. I started off the course showing you a picture of this pyramid. This is an ancient Mayan pyramid in Mexico. It was built somewhere around more than 1,000 years ago, perhaps around the year 800. And you can look at the geometry of this temple and from that understand that the people who built it understood the motions of the stars, at least as they appeared to move in the night sky. And they understood the seasons and they understood the motion of the sun. Okay? And so it's built in such a way that you can watch shadows creep down these steps in a way that almost looks like a snake at certain times of year. So it's pretty clear that people going back thousands of years thought that the night sky or what was going on in the heavens was an important thing. And they dedicated a lot of time and energy to sort of focusing on that and using it perhaps as a window into something deeper. So today, of course, we have our own sort of temples to the night sky in that we put telescopes up on top of mountains. The reason why we do this is if we go up on top of mountains, we're getting rid of some atmosphere. We're going up above at least some layer of the atmosphere. And a lot of times on mountaintops, if it's a high enough peak, then the atmosphere is pretty stable and doesn't roil around. I spent a little time telling the story of James Lick, who was this very wealthy person in California who ended up donating a good fraction of his life savings at the end of his life to build the first permanently staffed mountaintop observatory, professional observatory in the world that is known today as Lick Observatory. And you can go up there today, and it's still used. It's still a really important and vibrant research arm of the University of California today with updated telescopes and instruments, etc. But this thing got its start in the year 1888 on top of Mount Hamilton, which is not too far from San Jose. While that's an important research center for the University of California, it's not the premier research center in astronomy today. That would be reserved for the Keck telescopes. Let me go back. There's actually a pair of them. While Lick's first big telescope was 36 inches in diameter, the Keck telescopes are 10 meters in diameter. So something like 400 inches in diameter. So they're just giant things compared to those first telescopes, which were themselves very big. Okay? This is up on the roughly 14,000-foot Mauna Kea volcano on the big island of Hawaii. So it's basically the single tallest peak anywhere in the middle of the Pacific Ocean. Okay? And for that reason, there aren't other big mountains around to roil the atmosphere. And so it's a very, very clean atmosphere. You're up very high. It's a very dry place. And so it's a beautiful place to observe the night sky and to put giant monuments for understanding the cosmos. These things are gigantic. Okay? They're 8 stories tall. They each weigh about 300 tons. And the amazing thing is they operate to a precision of nanometers. Okay? They're precise to nanometers in its pointing and aligning of the mirrors within things that weigh 300 tons that are 8 stories tall. So it's incredible sort of confluence of engineering and science and dedication that go into operating these things. To give you a sense of this, it's hard to see in this light, but There's a pickup truck circled right here. One of these really big pickup trucks is right there. These things are just gigantic. In roughly 2020, we are endeavoring to build an even bigger telescope that will also be up on Mauna Kea. And this telescope is going to be 30 meters in diameter. And I'll return to this in a little bit later. But there's, I'll talk a bit about, we've talked a bit about things we've learned from telescopes like the 36-inch and now the 10-meter telescope. And there's a lot of questions that remain unanswered that we're hoping are going to be answered by this gigantic 30-meter telescope that's being built now. So if we were to give an overview of scientific cosmology, I've shown this thing before, but let's just remind ourselves what we think is going on. Okay, so we think that space and time began about 14 billion years ago in an event that we broadly call the Big Bang. Okay, it's just a name for it. But we think very early on the universe was small and very hot. And in those first few seconds after the Big Bang, eventually emerged the very light elements of hydrogen and helium. And that's about it. And then from this beginning, which turns out was extremely simple, it was just hydrogen and helium gas, eventually the universe kept expanding and cooling down. And over about 14 billion years, all the complexity we see around us today, this vast network of galaxies that we've talked about, the galaxies themselves, which are filled with stars, and around some of those stars, planets, etc. The fact that we've been able to sort of unpack this, to figure out that this is what's going on in the universe that we live within is really quite amazing. Okay, if you step back and think about what we have to work with, it's really an astounding problem. Okay, I showed this image before also on the first day of class. This is an image of the night sky taken at dawn in Central Africa. And you can imagine people living 100,000 years ago looking up at the night sky and seeing a picture that's not that much different than this. Now they could see very clearly that there's the sun up there, right? The sun rises and sets, goes up high, goes down low. And eventually you might start to recognize that in certain times of year the sun rises up higher in the sky than others. There are these other things up in the sky that are bright, like Venus and Jupiter. Okay? They seem very important, but as we understand now, they're actually very, very small compared to, say, the actual physical size of the brightest stars. The only reason why those things appear bright is they're extremely close compared to those stars. And in fact, these stars are really suns in their own right. So people began to sort of build models to make sense of what we see in the night sky. And of course, ancient Greeks like Aristotle built pictures, had a model for what he was seeing. He said, look, I know exactly what's going on here. Of course, the Earth is fixed and immovable. And all of this stuff up in the sky is orbiting around us every 24 hours. The sun comes up and goes down. It's orbiting around the Earth. The stars go up and come down. They're also orbiting around the Earth every 24 hours. And the Venus and Jupiter, the wanderers, the planets, are also orbiting around us, but just at a slightly different speed, and that's why they move around like that. Aristotle would have very clearly seen the Milky Way every night it was clear because he didn't have a lot of light pollution to deal with, right? His skies would look like our skies look like out at Joshua Tree National Park, right? Even in Athens, downtown Athens, right? It was dark. There were no streetlights. So he would see the Milky Way, but he didn't know what to make of it. And in fact, he thought that the Milky Way was an atmospheric thing. He thought that it was probably some kind of feature in the atmosphere of the Earth that was below the orbit of the moon, that was just kind of a feature. Maybe it was burned in there in some way. But he really had no idea what the Milky Way was. If we fast forward almost 2,000 years, Galileo Galilei, looking at this sky, would have said, no, that's not exactly what's going on. He would have said, what's actually going on is we are going around the sun, as are Venus and Jupiter. And the reason why it looks like things are rising and setting at night is that the Earth is spinning on its axis. And all while it doesn't feel like it, we're spinning. One of the things that Galileo had, in fact, the major thing that Galileo had that Aristotle didn't have, was a telescope. And when he pointed his telescope at Jupiter, he didn't just see that white light, but he was able to show that this white light always had these other little white lights near it. And as he tracked it night after night, and hour after hour, you could see that these white things looked like they were going around Jupiter. And of course, today we can track that very carefully with the kind of telescopes that you sometimes will get to use. And you'll see they'll pass in front. You can see them casting shadows on Jupiter. That Jupiter, in fact, has its own moons. And when Galileo realized that Jupiter had its own moons, suddenly all of this kind of philosophical argument that everything ought to orbit around the Earth just kind of vanished, right? Because it was sort of clear. It was clear by eye, any person who looked through that telescope could see that not all heavenly bodies orbited around the Earth. And this was sort of one brick of the foundation that Aristotle had built began to crumble. And soon a lot of other pieces of evidence mounted that this idea that everything goes around the Earth just doesn't work. Galileo would also observe that Venus, in fact, wasn't a pinprick of light, but that it went through phases as it orbited around the sun, just like our moon goes through phases as it orbits around the Earth. And again, this was sort of concrete evidence that things were going around the sun and not around the Earth. So now we have a model where the Earth is moving and spinning and the stars are distant suns. The other thing that Galileo did is he pointed his telescope over here at the Milky Way. And he saw that the Milky Way actually broke up into the light of countless stars. When he looked at it with his telescope, he could see not just this smooth, smeared out light of this band, but he could see that there were certain regions that the reason why it looked smooth and smeared out was just because there were so many stars there, your eye couldn't differentiate them. But with this, basically his expanded pupil of the telescope, it allowed him to separate that light into sort of separate pinpricks and demonstrate that, hey, the Milky Way is actually made of stars. But the question of the importance of this Milky Way remained unanswered. Okay? It was clear that what it was now was a collection of stars. But what did that mean for the grand structure of the universe? Now, eventually, over the course of years, people would begin to study more carefully this and began to realize that we were embedded within a disk of stars, and when you saw this thing in the sky that looked like a band, it was just because you were looking into the disk. The next big breakthrough came when Edwin Hubble was looking at the night sky. So this is a different picture of the night sky. This is now, we've moved from Africa to Chile. This is a picture of the night sky from Chile. Actually, I'm going to turn the lights down a little bit. I know you're not going to fall asleep. Okay, so this is a better picture. Yeah, it looks better now. So this is a picture of the night sky from Chile. Okay, and so Edwin Hubble here around the year 1920 was looking at a particular smudge up here. You see this thing here? That's the Andromeda Galaxy. Of course, at the time, it was just called the Andromeda Nebulae. People weren't sure exactly what it was. But using the 100-inch Hooker telescope, Edwin Hubble was able to detect individual Cepheid variable stars in Andromeda and demonstrate, based on the period of their oscillation, he knew how intrinsically bright they were. And from that, he was able to infer a distance to Andromeda and demonstrated that it was more than 1 million light years away. Much, much, much bigger than the understood extent of the Milky Way disk. And so what this then implied was that the universe was not only our collection of stars, but in fact, the universe was made up of a bunch of other island universes in their own right. And that these stars here, these little pinpricks here, were stars within our own galaxy. And when we view them, we're just looking up out of the disk. Okay, if you look away from where the disk of the Milky Way is, they're just in some other direction. Whereas nebulae like this are other spiral galaxies in their own right. So now we understand, of course, that when we look up at the night sky, what we're seeing is an edge-on disk of stars. So this is what we see, but what's really there is this vast, vast disk of stars that's 100,000 light years across. And it's amazing if you think about it, that every star we can see by eye at night is within a bubble of about this size. Okay, the nearest star to us that we can see by eye is 4,000 light years away. And in fact, the vast majority of stars that we see by eye are much, much closer than that. It's just an extremely bright star that's that far away. So, and to put it another way, there are about 6,000 stars over the whole globe that are visible by eye, that you can see with your naked eye on a very dark night, where there are about 100 billion or more stars in the Milky Way galaxy. So when you look out at the night sky, even though it seems like the stars are sort of limitless and uncountable, that's actually only a teeny tiny sliver of all the galaxies, all of the stars that actually are there in our galaxy. So we have a situation now where we live in a Milky Way galaxy, which is one star. Sorry, the sun is just one star. The Milky Way galaxy has over 100 billion stars. And we now realize that the universe we inhabit contains over 100 billion galaxies like ours. So one of the really amazing ways that you can sort of see this is in this picture. This is a Hubble Space Telescope image of a relatively nearby galaxy that's only about 300,000 light years away. Okay? Now, you're looking at a face-on disk that's not that much different than the Milky Way, and this dark stuff is dust that's sort of casting a shadow with the smeared out light behind from their stars. Now look carefully here, and you see all of this stuff like that, right? What those are galaxies that are like this, they're just behind it. Right? So the universe is just filled with galaxies like this. And if you look deeply enough, you'll see them kind of everywhere. The crazy thing is you can see them through this galaxy, right? You see what I'm saying? If you look closely here, there's these things. You're seeing, if you look through the galaxy, you're seeing them behind this other one. And that's how incredibly just sort of plentiful they are. There's just billions and billions of them out there, and each one of these things contains 100 billion or more stars. So it's incredible. And discovering this, right, has been this trajectory from starting with the naked eye astronomy to Galileo's first telescopes to those bigger telescopes. We have a telescope in space like Hubble, which allows us to make these kind of images. So it's really profound. This is a movie of the night sky, a zoom in to one of the deepest images that Hubble has ever taken. What we're going to do is zoom in to deeper and deeper images of the night sky in a spot that looked just basically dark. But if you look deep enough, you begin to see that there's always more there. You just look back in time, back in time, back in time, and eventually you arrive on extremely crowded regions. So this thing here is called the Hubble Ultra Deep Field. It's a specific region of the sky where the Hubble Space Telescope basically pointed for 2 weeks, keeping the shutter open on its cameras for about 2 weeks, collecting light to take this incredibly detailed image. These galaxies are so far away that we're seeing them back in time when the universe was young, and that's why those galaxies are kind of messed up looking. The ones you see that are sort of tinted red are the ones that are the farthest away, that are from the earliest times, and that's because the universe is expanding. So the things that are farthest away are expanding away from us faster. As they expand away from us faster, their light redshifts. Okay? So where they might be glowing blue if you were with them, by the time we see their light, that light has been redshifted and now is red to the eye. So how did the universe get to be so lumpy? How is it that there are all these galaxies everywhere? What drove that? So this is one of the big questions we have today. Why are there so many galaxies? So one of the things, this is a map of the large-scale universe, and I've shown you maps like this before. This is a deep, large-scale map of the universe, where this is today. And as you look along this direction, you're looking at galaxies that are farther away, and therefore we're seeing them back in time. And this is sort of a couple of billion light years across. And what we see as we look at galaxies that are farther away, we see the universe is less structured. That is, it's not as clumpy as it is today. There aren't as many galaxies, and those galaxies are not as clumped together as they are today. So one of the things that's amazing is one of the questions that lingers is, how do you start off, like how do you have an early universe that's incredibly smooth, and from that early smooth time, build up a universe that's as clumpy and has as much structure and galaxies in it as we see today? The answer to this problem, okay, the clue to the answer to this problem started here in this clump of stuff in our local neighborhood. It's called the Coma cluster of galaxies. The Coma cluster is a group of galaxies that are sort of swarming around each other like bees in a hive. This is a picture of it. And in 1933, our friend Fritz Zwicky was studying the Coma cluster of galaxies, and what he was doing was measuring how fast they were moving relative to us. So he's using their line of sight velocities, the redshift of their light, okay, to measure their relative motions to each other. What he found is that they were moving around much faster than they should have been if the only gravity that existed where the light could be explained by the light that he sees. Okay? And from this, he proposed the idea that there's actually an additional bunch of mass out there that he called dark matter. And this was the first piece of evidence that we had that there was something else out there in the universe that was tugging on things gravitationally. And what he found is that he needed more than 10 times as much extra mass out there than the stuff we could see. Now, not that many people took this result very seriously as being globally important. But if we flash forward to around the year 1965, people like Vera Rubin were studying the speeds of galaxies, but not how fast they were moving relative to us in a bulk sense. But technology had improved to the point where she could actually measure how fast it was spinning around itself on its axis. So we believe that spiral galaxies are spinning around, and that's why they're flattened into disks. And the speed with which they're spinning around correlates with how much mass there is. Now what you would expect was that the speeds of the stars near the middle of the galaxy, where it's bright and there's lots of stuff, would be fast. But as you go away from the center of the galaxy and you start running out of matter, the motions of those stars should go down. Okay, this is what's seen in the solar system. Okay, Uranus and Pluto are going around the sun much more slowly than the Earth or Venus. And that's because they're farther away from that main point of mass. So this is what Vera Rubin and other people thought would happen when you looked at the speeds of stars spinning around galaxies. But that's not what they found. What they found was that as you go out from the edge of galaxies, the stars keep right on trucking. The gas clouds out there are moving around very quickly compared to what you would have expected. And this isn't just one galaxy, okay? It's every single galaxy we look at. If you go out far enough in its rotation versus distance plot, you will see this evidence for this extended component of mass. The same is true for the Milky Way. We see it for M31, and we see it for lots and lots of galaxies. And so this was yet another piece of evidence that there was this missing mass out there, this dark matter. Okay. So what's shown here, I showed this movie before, but just to remind you, amazingly, if you throw this additional mass in the form of this dark matter, what you find is that you can explain this conundrum about how the early universe could be so smooth and yet be so clumpy today. In order to go from smooth to clumpy, you need gravity to make that happen. But if you only put in the same amount of stuff in the universe that we see in terms of visible matter, it's nowhere near enough to go from smooth to clumpy. You have to have this additional mass in the form of dark matter that allows galaxies to grow over time as quickly as we see them do. And in fact, when you put this in, it's amazing. You not only get qualitatively the right structure formation, but you get quantitatively the right structure in the large-scale universe. You get structures of galaxies strung out along filaments with big open voids. You get smooth early universe and clumpy late universe, very, very similar to that universe that we actually see. So the amazing thing about this picture is it seems sort of crazy when you first sort of seeing evidence for it. Okay, there's this missing mass. Maybe it's a bug. Maybe it's an error. But as you start looking at lots of different pieces of evidence, it all begins to sort of point to a single kind of picture. And it's these kind of observations that sort of allowed us to construct what we believe is a consensus model, a current paradigm for what the composition of the universe is today. And amazingly, the universe is made mostly of stuff that's very foreign to us. I'm going to turn these back on because even I'm starting to fall asleep. That's not good. Right, so 25%, so only 5% of the universe is in the form of this mass of normal stuff that we're familiar with. Anything on the periodic table, anything made of protons and neutrons is this 5% wedge. Where 25% of the universe is in the form of this dark matter. This stuff that was hinted at by Zwicky, found more evidence for by Vera Rubin, and today there's just mounting evidence that this stuff is out there. And finally, there's this giant chunk of the wedge that we call dark energy. And the dark energy is the weirdest stuff of all. Dark energy is the name we've given to the stuff or the phenomenon that's driving the universe to expand at an accelerated rate today. Okay? So if you look at some estimate of the size scale of the universe versus time, it looks like today the universe is actually speeding up in its expansion. And that's a very strange thing. Okay? Naively, you would think the universe should be slowing down in its expansion because there's mass in the universe and the mass wants to tug on everything else and it should bring things back together. But that's not what's seen. What's seen is that the universe is actually speeding up in its expansion. And if we can account for this in the context of general relativity, we can put terms in the equations that make it do the right thing. But physically, it's a very weird thing. And understanding what this dark energy is something that is unsolved. And it is such a big puzzle in physics today that it may not be solved in 100 years. I mean, it's a very, very strange puzzle. Unlike the dark matter puzzle, which could be solved in 10 years. You know, it's sort of a more solvable problem, perhaps. So we're back again to this picture that I started with. And you know, let's review sort of what we know, right? We have this idea that the universe is expanding. And again, that's in the context of this picture. The universe is expanding. It is, at early times, it was very small. And today, it's getting bigger. Because it was very small in the very beginning, it was hot. In the very, very beginning, it was so hot that even neutrons and protons couldn't stay together. That the neutrons and protons were moving so fast with respect to each other, if they formed, they would just collide with each other again, and the quarks that make them up would break free. But eventually, the nucleons stabled out. The universe expanded enough that these collision between particles hardly ever happened, and you had neutrons and protons. And eventually, things cooled down enough that the light nuclei could begin to form. And specifically, I'm talking about hydrogen and helium. So within the first few minutes after the Big Bang, things had cooled down enough that nuclei could begin to settle out. And hydrogen and helium were formed. And if you kept everything dense, if you kept a bunch of neutrons and helium nuclei and hydrogen nuclei together in a dense state for a long time, eventually heavier nuclei would build up. Kind of like what happens in the centers of massive stars. But that's not what happened in the early universe because the early universe was expanding. And so those conditions for making heavier nuclei lasted only a fraction of a second, and then the universe expanded so much that that couldn't continue to happen. And so what the universe was born with was basically nothing but the lightest nuclei, hydrogen and helium, and virtually nothing else. But of course, when we look around us today, we see the universe has all kinds of elements in it, not just hydrogen and helium. So where did all that the stuff that's not hydrogen and helium come from? Does anyone know? Where did all the stuff that's not hydrogen and helium come from? Good, from stars. Very good. It was forged in stars. So the Big Bang dealt us this, but from this, the universe started to build galaxies and stars. And in those galaxies and stars emerged the heavier, more complex elements. Another thing, so something that we've come to realize is that the universe effectively has been a galaxy factory for about 14 billion years. One thing it's been doing very well and very efficiently is making galaxies. So even though the universe is expanding, there are certain regions of the universe that have enough gravity that they break off from that expansion, fall back together, begin to collect gas. That gas turns into stars, and those stars start forming. So we look around us today, there's just a vast complexity of galaxies all over the place. And of course, because they're galaxies, they have stars, and these stars are what's forming the heavier elements. Okay? And we know that on at least one star in one galaxy, we got a planet with a lot of water, liquid water. And on that planet, we have a lot of carbon, nitrogen, oxygen, and phosphorus, in addition to the hydrogen that was dealt us in the Big Bang. And as many of you probably know, hydrogen, carbon, nitrogen, oxygen, and phosphorus are the key elements for DNA. Right? So on at least one planet, around one star, in one of these hundreds of billions of galaxies, the universe has managed to produce elements that have come together with such temperatures, etc., to do pretty complex things. Okay, I like this thing in particular. It's my daughter. So I like this thing in particular. So, how does this happen? Okay, here's a picture of a galaxy that's not too far away. It's called M81. Now, it looks like it's on fire, right? It looks like it's spitting fire out of its edge. That's not really what's going on. What's going on is it's an edge-on galaxy, and there's a lot of dust. And this red stuff is glowing hydrogen gas that's being expelled out of the galaxy. What's happening in this galaxy, it turns out it's forming stars at a really rapid rate, something at an unusual rapid rate. And when very massive stars form, they don't last very long, and they blow up as supernovae. So when a bunch of supernovae blow up at roughly the same time, they create what are called galactic chimneys and drive tremendous amounts of gas out of their tops and bottoms. This is just where the stuff can escape. It's hard to blow gas out in this direction, but it goes out the easiest way it can. Now, supernovae are where the heavy elements get made, are where the carbon, nitrogen, oxygen get made and released back into the universe. Remember, these are the ingredients for DNA. Now, normally, right, this gas, in fact, is blowing out. It's blowing out at incredible speeds, sometimes thousands of kilometers a second. Really, really high speeds. Such high speeds that naively you would think it would just be blown out of the galaxy, never ever to return. But that's not what we see. Okay, we see a lot of evidence that, in fact, these heavy elements don't just blow out forever, but they circle back down and they fall back in. This is very important. Okay? Because the very first stars to form are all hydrogen and helium, which means any planets that form around them would also be hydrogen and helium. There's no heavy elements, right? They're just forming after the Big Bang. But when the first big massive stars blow up, they create the first complex heavy elements in the universe. And they want to get blown back out of the galaxy, never to return again. But instead, some of this stuff falls back down, okay? Gets incorporated into the next generation of stars. And that next generation of stars now has carbon, nitrogen, oxygen, phosphorus around it. And the heavier elements, like silicon, can form into rocky planets. Okay? The oxygen can combine with the hydrogen to make water. And you begin to form planets that have the right conditions for very complex and interesting things to happen. So the question remains then, why does the stuff come back? And the amazing thing is that based on models that we've run now, the reason why the stuff comes back is there's actually a lot more mass there than you think. There's all this dark matter there, that creates a strong gravitational tug for the stuff that's getting blown out to fall back in, to get reincorporated into the next generation of stars that then get to seed complexity around those stars. So what this means is that if you think about it, we need dark matter in the context of this standard cosmology. We need this mysterious stuff to make galaxies in the first place, to allow complex chemistry to arise around stars, and therefore to enable life itself. So this universe that we live in that seems sort of random, okay, if you think about the ingredients that we were given and the pictures that we're trying to develop to make sense of it, once you step back a little bit, you realize that if all of these ingredients weren't there, things may have turned out quite a bit differently. Another thing we've come to realize is that as you track back to the very beginnings of the universe, it's obviously very hot. And as it gets hotter, what you're doing is you're probing very, very high energy scales. High energy scales that are basically dominated by the smallest scales of matter. The fundamental forces that we think govern everything, the fundamental particles that we think make up everything. Okay? Now, the cool thing about this is it creates this kind of intimate connection between the smallest scales in nature and the largest scales in nature. Okay? There's a giant particle accelerator at CERN that's happening right now that's about to get turned back on called the Large Hadron Collider, which is huge and speeding up fundamental particles and slamming them together at incredibly high speeds, almost the speed of light. When they hit each other with such velocities that they create temperatures that have not existed since the Big Bang. So effectively what this collider is trying to do is recreate conditions that have existed only in the Big Bang, here on Earth, in laboratories on Earth, to allow us to sort of test important physics that should have been going on at these early times. So it allows us to kind of look back to the early universe, building a little laboratory on the ground, and asking ourselves, well, maybe dark matter will fly out of this collision. So one thing they're trying to do in these laboratory experiments is actually to create dark matter particles out of nothing, well, out of these normal particles. And if they see that, that will be a clue to how dark matter was created in the early universe and why dark matter pervades the universe today. So I haven't talked much about that, but there is this kind of really amazing link between the largest scales in nature and the smallest scales in nature that cosmology sort of brings together, unites the fields of astronomy and particle physics in this sort of deep and interesting way. So I started, I'm going to turn the lights back down now, so please don't fall asleep again. Did I say again? I didn't mean again. So where did we start, right? Where did we start? We started something like 100,000 years ago, right? With people living on this Earth, living on this planet, that had benefited from the fact that there were complex molecules around, complex atoms around, liquid water. And eventually, after about 4.5 billion years, give or take, of evolution, this kind of intelligent thing was around. And these people, okay, probably as smart as us, okay, almost certainly not dumber than us, were walking around and looking up at the night sky and trying to make sense of this spinning globe that they found themselves on. And the main tool they had to look up at the heavens with was the dilated pupil of their eyes, which is 0.3 inches in diameter. And with that tool, and armed with kind of a big brain, they eventually built models that were amazingly observant, right? I mean, they understood very early on, without any aids from technology, the origin of the phases of the moon, for example. And they had a pretty good sense of other sort of physical phenomenon. But a real breakthrough came in the year 1620, when Galileo extended the senses of the human pupil using something that was now 1.5 inches in diameter, right? It's a pretty big jump. And with that, he was the first person who ever lived to see new stars, to see the moons of Jupiter, to see the phases of Venus. And with these observations, suddenly the universe opened up. And he was able to see farther than anyone had seen before. If we flash forward to the year 1900, that's when James Lick's gift was put forth on Mount Hamilton. It was with this telescope that people like Keeler and others began to decipher the nature of these smudges up in the sky. And they began to realize that it actually went beyond the stars that Galileo had told us about, but it was these smudges were actually galaxies in their own right, like the Milky Way, that the universe was even bigger than even people like Galileo had imagined it to be. But the story doesn't end there, right? That's the year 1900. Let's rescale this thing down again. So there's Lick's telescope. In 1993, when the Keck telescope came online on the top of Mauna Kea, it was the largest optical infrared telescope in the world, and it still is. No one had any idea that the universe was accelerating in its expansion. We had no evidence of that. But thanks to detailed observations with Keck to get redshifts of galaxies, we learned something crazy, that the universe is in fact accelerating, and that there's this entirely unexpected thing out there called dark energy that we're still trying to grapple with. It's with Keck that we've come to understand the nature of dark matter in a deep way. Again, these were things that were really certainly not thought about in the year 1900. And I'm, of course, using this as a proxy. There are many, many telescopes right now operating that are doing this kind of thing. And so I showed you this picture before of the 30-meter telescope that we're hoping to build. And while I would like to tell you precisely what we're going to discover with that telescope, I think it would be a little bit naive of me to do that. Because if the universe has taught us anything, it's every time we'd look deeper with bigger tools and more powerful ways to extend our senses, we've discovered something that's mesmerized us and surprised us and humbled us. And so maybe we'll come back in 10 or 20 years and we'll be able to add that to the slide too. Okay. Thanks very much. Hope you like the course.